Hello everyone, this is S. AKILA, Assistant Professor, PG and Research Department of Chemistry, Theivanai Ammal College for Women, Villupuram. Today we are going to see what is bimolecular nucleophilic substitution reaction, that is SN2 reaction. After studying this topic, we shall be able to understand the mechanism, kinetics and stereochemistry and what are the factors affecting SN2 reactions. Before we enter to the topic, we should know what is substitution reaction. Substitution reactions are type of organic reaction in which any atom or group is replaced by other atom or group. Here the substrate or CH2X react with the attacking reagent Y that produce the product or CH2Y. Here X is replaced by Y, that is substitution reaction. When the substrate is attacked by nucleophile, nucleophilic substitution reaction will occur. Then what is the nucleophiles? Nucleophiles are electron donor spaces. They may be neutral having non-bonding lone pairs or negatively charged spaces. Trimethylphosphine, dimethyl sulfur, ammonia, water is the example for neutral nucleophiles, and alkoxide, hydroxide, cyanide and amino groups are example for negatively charged nucleophiles. The bimolecular nucleophilic substitution reaction which follows second order kinetics are known as SN2 reactions. The rate of the reaction depends upon the concentration of the substrate and the nucleophiles. Here the rate equal to K substrate and nucleophiles. Here the square bracket represent this concentration of the substrate and the nucleophiles. These reactions are completed in a single step by displacement of leaving group by the nucleophiles. SN2 reactions always goes through possible transition state. The nucleophile attack the substrate carbon 180 degree away from the nucleophiles, resulting the inversion of configuration. The reaction between methyl bromide and a strong nucleophiles such as hydroxide ion is a good example for SN2 reaction. Here the OH minus ion attack the substrate carbon 180 degree away from the bromine groups, so that form the transition state. The new COH bond formation and CBr bond breaking occurred simultaneously. At one stage, both Br and OH are partially bonded to the central carbon atom, which is known as a transition state. The energetic OH ions approach the CH3Br, that is the substrate molecule, from the opposite side of the bromine to avoid the repulsion between OH and Br minus ions. The reaction is thermodynamically favorable only when the stronger base is displaced by a weaker base. The transition state represented an energy minimum on the reaction coordinate. The energy difference between the transition state and the starting material of the reaction is known as activation energy. That is the energy difference between transition state and the starting material of the reaction is known as activation energy. The reactant are slightly higher energy than the product. This is known as exothermic reaction. Here we can see the energy diagram of the SN2 reaction. Here the transition state having higher energy state. The energy difference between the reactant and the transition state is known as activation energy. The configuration of the chiral carbon is inverted during the reaction is known as Walden inversion. Walden inversion reactions. The nucleophile attack the opposite side of the nucleophiles. This is the main reason to result the inverted product will form. Here we take a chiral carbon. Chiral carbon, which means the carbon is bonded with 4 different groups. The hydroxy groups approach the central carbon to form the transition state. After the leaving group departs, the product will forms. If the reactant is S configuration, the product will be S. If the reactant is S configuration, the product will be R. The inverted reaction will occur if Walden inversion take place. Stereochemistry of SN2 reaction. SN2 products are stereospecific because stereoisomeric reactant give stereochemically different product. They are also stereoselective because they are exclusively only one of the possible pair of enantiomers or one of the possible diastereomers will form. Here the good examples are cis-1-chloro-3-methyl-cyclopentene react with hydroxides which undergoes SN2 reaction to form trans-3-methyl-cyclopentanol. On the other hand, -2-bromo-octane react with hydroxy groups to produce plus 2 octanol. Both the product gives inversion in configuration. These are the good example for SN2 reaction. Various factors will affect SN2 reactions. These are solvent, strength of the nucleophiles, leaving groups and the substrate. Polar protic solvents such as DMSO favors the SN2 reaction, and strong nucleophiles give faster the reactions, and better leaving groups accelerate SN2 reaction. The best leaving groups are weaker base. For example, iodide ions are better leaving groups than the chloride ions. The decreasing order of leaving groups is given here. The methyl groups is methyl and tosyl groups are best leaving groups compared to iodine, and then followed by bromine and chlorine and fluorine. OH and NH2 are good nucleophiles but not a good leaving group. Substrate. Less steric hindrance substrate faster the reaction. The reaction rate of SN2 reactions will be methyl halide followed by primary alkyl halide and then followed by secondary alkyl halide, finally tertiary alkyl halides. The steric hindrance increases will reduce the reaction rate. For example, methyl bromide reaction rate is less than 1000. It is reduced into 50 when it is the substrate is ethyl bromide, and for isopropyl bromide reaction rate is 1, and for the tertiary butyl bromide it is reduced into 0.001. So the steric effect increases, the rate of the reaction will decreases. To summary and quick recaps, SN2 reaction follows one step mechanism. It is a bimolecular reaction. Backside attacks is only possible, that gives inversion of the configuration. Walden inversion proves the stereochemistry of the SN2 reaction. Reactivity depends on the substrate, nucleophiles, leaving group of the solvent. In chemistry, even a single flip can change everything. Thank you.